Gonna start.
All right, before I forget, let me first just say this test one. You pretty much know what it is now. It's going to be March 16th. That's a Wednesday. Not Wednesday coming, but a week from Wednesday coming. So I'll post review problems on my website for you guys to practice. But it's going to be roughly March 16th. The plan is to actually finish all the material for that today, actually. So, but yeah, that's going to be March 16th. I had your homework and quiz to give back, but I forgot to bring them with me. They're actually in the other building. So if you want to pick them up today, you can. You just follow me back to the tutoring center later. But yeah, so okay, let's pick up where we left off. All about determinants and inverses. We had an example, A equals 1 minus 2, 3, 2 minus 1 minus 1, minus 3, 1, 4. We're actually finding the inverse of that using row operations. Did anyone actually finish it? What's A inverse here?
I got some fraction.
You did it? What? Give me the first row.
Minus 12, 24.
Minus 12, 24.
Then minus 5, 13, 7. Minus 1, 5, 3.
That's it?
Yeah. That's inverse.
Does everyone agree? How could you check if that's true?
Well, 2 multiplied by 8.
Okay, so let's multiply by 8.
I might not correct.
So if I take A times your proposed A inverse, I would get 1 minus 2, 3, 2 minus 1 minus 1, minus 3, 1, 4. So we would have minus 12 plus 10 minus 3. That would be in the first position. What's that? That's already not 1, right?
Yeah.
So
I did it, but I didn't follow the way.
I multiplied by 4. I got the fraction, but then I multiplied by 4.
wait, so you got fractions in this, but you just randomly multiplied everyone by 4?
Because everywhere was a minus 12 over 4, 24
Well,
over 4.
you can't actually do that. So you'd have to put the 1/4 out here.
Oh,
But this would be minus 12 plus 10 minus 3. That would give you 15, which even if I divide that by 4.
still not.
You want me to give you what I have?
What do you have?
It's negative 3 over 4.
Here, in the first position?
Yeah.
Minus 3 over 4. Okay.
11 over 4.
Positive 11 over 4.
7 over 4.
Yeah.
Negative 5 over 4. 13 over 4. 5 over 4. Negative 1 over 4. 5 over 4. 1 over 4.
Good. And I guess we didn't like the over 4 over 4. It's okay to take out a fraction if you don't like it, but you have to put it here. Like you can't just multiply everyone by 4. It doesn't work that way. So let's actually try that. In fact, let's actually keep this 1/4 out here just to make our lives a little bit easier. Minus 3, 11, 7, minus 5, 13, 5, minus 1, 5, 1. And I just know whatever I'm getting, I'm going to divide by 4 in each element. So here we would have minus 3 plus 10 minus 3 plus 10 minus 3.
Yeah, this one.
Then in the second position, I would have 11 minus 26 plus 15, right? Then I would have 7 minus 10 plus 3. And in the second row, I would have minus 6 plus 5 plus 1. I would have 22 minus 13 minus 5. I would have 14 minus 5 minus 1. I have 9 minus 5 minus 4. Minus 33 plus 13 plus 20. And minus 21 plus 5 plus 4. Do those give us what we want?
Row 2, third column. Was that 14 minus 5 minus 1?
Row 2, this column, it's
Not
2,
zero.
2 times 7 is 14, minus 5 minus 1. Yeah, so
That won't work, right?
So can we just use the 1 over determinant of A times the adjoint of A and then find the inverse that way?
we didn't do that way yet, but yes, you could do that. I'm going to show you guys that way today, but I'm thinking you guys need work on your row reduction.
Professor?
You see, we have those
Yes.
other techniques we can use to make
It's
this
just a
out.
question about the row reduction. So like I was checking out the lectures, last lecture online. And,
Yeah.
Your method where you resort to fractions at the end, is that like a conventional method by all textbooks or is that your thing?
No, that's just me.
Okay. What's more effective though? Because I feel like I've tried with the fractions and I feel like it's more prone to mistakes but shorter steps. But then your way, I don't know, it's like a lot of steps and I'm not sure like.
It's up to you. I don't particularly care what you do, but it's my recommendation that you avoid fractions. If you like working with fractions, that's fine. Let's actually find to see where people are wrong, because we're actually going to use this guy in other examples, so we should find it. So how do we get to A inverse? You augment this guy with the identity, right? And then you just start to do your stuff. So what are we going to have here? So I'm going to say something like row 1 minus row 2. Or row 2 minus row 1, it doesn't matter. Minus 2 times 2 row 1 minus row 2. So I multiply this by 2, minus 2, 0. This is minus 4 plus 1. This is 6 plus 1. This is 2 plus 0. 0 minus 1. 0 minus 0. And here I would say 3 row 1 plus row 3.
Is that positive?
I took 2 times this minus that, right? So that's minus 4 plus 1, which is minus 3. Here I'm going to take 3 times this plus that, 0. 3 times this is minus 6 plus that. 3 times this is 9 plus that. 3 times this is 3 plus that. 3 times this is 0 plus that. 3 times this is 0 plus that. So what I'm going to do here is leave this guy. So I can multiply, say, row 2 by 5. 0 minus 15, 35, 10 minus 5, 0. Multiply row 3 by minus 3, 0, 15, minus 39, minus 9, 0, minus 3. I'll put back one of these guys, maybe the smaller one. And then for this one, I'm just going to add those two. 0.00 minus 0, and minus 39 plus that gives me minus 4. This would be, if I add those two, I would get 1, minus 5, minus 3. We're okay so far, right? So this would give us what? Now what do I want to do?
Root, oh, reduce root 2.
Reduce row 2? What do you want to do? Maybe we want to kill this guy? So how do we do that? I can multiply that by 3. 3 minus 6, 9, 3, 0, 0. Row 1 times 3. And this one I'd multiply by 2. Row 2 times 2. This one I can let hang out for a while. Here, I would do this 0, 0, minus 4, 1, minus 5, minus 3. This would be 0, 3, 7, minus 2, 0. And now I would just add these two. So that would give me 3, 0, minus 5, minus 1, 2, 0. What do we have now? How about we try to kill this 7 and kill this 5? Do that in 2 steps. Which one I want to kill first? Doesn't really matter. I can multiply this. Let's kill the 5 first. So I'm going to multiply this guy by 4 and this guy by 5. So multiply this by 4, I would get 12, 0, minus 20, minus 4, 8, 0. Multiply the last one by minus 5, I would get 20 here. Did I copy down the right thing? I copied this here. Okay. Minus 5 times this is minus 5 plus 25 plus 15. Let's add those two. So I would get 12, 0, 0, minus 9, 8, and 25, that's 33. Let's use this opportunity to kill the second row as well. Okay, so that's what the first row is going to become. So how would I do this? Let's multiply this one by 4. So you get 0, 12, 8. 4 times minus 8. 4 times 4, 4 times 0. And multiply this one by, say, minus 7. So now, I'm not going to need this for anything else, right? So I can just actually right away now just make that the 1, 0, 0. So this is minus 9 over 12, 33 over 12, 15 over 12. So this is row 1 divided by 12. Here I'm going to add these two, so I get 0, 12, 0. That's minus 17, 37.
Minus 15.
Where?
You add second and third row, right? It's minus
Oh,
15.
I was adding the
Yeah.
second and first row. Okay, I'm adding the second and the third. Right. So this is minus 15. This would be 39, right? And that would be 21. This is row 2 and 3. And at this point, I guess I could divide this guy. So then I want to divide by minus 4, minus 1 over 4, 5 over 4, 3 over 4. And take one more step to divide this guy by 12. Sorry. So what do I have in the first row now? What is that, minus 3 over 4? What's the other one?
11 over 4.
Come again? 11 over what?
4.
11 over 4?
5 over 4.
5 over 4?
Minus 5.
So here I'm going to divide through the second row by 12 now. So if I take minus 15 over 12, what do I get?
Minus 5 over 4. 13 over 4. 7 over 4. Minus 1 over 4. 5 over 4. And 3 over 4.
Was that what you had, or?
No, it's, I made a mistake somewhere.
I made mistakes in one number, so I corrected it.
Let's actually check.
I checked them both. It's correct.
You check this?
Yeah, I solved it. I find a mistake in my solve and change it.
Okay, so that's actually it. I'll take your word for it if you checked it. Okay, so that's A inverse. And this is the row reduction method to find the inverse. Yeah. And yeah, as I mentioned before, that saving for fractions at the end, it's a recommendation. It's not like you have to do it or anything like that. Personal preference. It's just that in my experience, you know, students mess up with fractions more than they mess up with the whole numbers. So I normally tell them to do that. But, okay. Did we do the inverse of 1, 2, 3, 4, the 2 by 2?
Yes.
We actually did that?
Yeah.
What did we say the answer was?
Negative 2, 1, 2.
Was negative.
Negative 2, 1, 3 over 2, 1 over 1.
Because I'm going to be using these guys again in further examples. So make sure you have these guys handy. Because I'm going to be asking you about them. Okay. I'm going to show you another way to find the inverse, which some people are mentioning about the adjoint matrix. But do I want to mention this first? Maybe I should mention that. Note. Just want to make sure you know. there would be no other answer for A to get its inverse. In fact, there's a theorem. The inverse of a matrix A if it exists is unique. Let me write this out in a way more conducive to, for example, if you want to prove that something is unique. Usually, a very typical way to prove that something is unique is to prove that there's more than one guys that do the same thing, and then prove that they're actually equal. Right? So let me just write that out. I.e., if B and C are inverses of A, then B must be equal to C. Right? So no matter what you do, how you find it, whether you use fractions at the end or at the beginning, it doesn't matter. At the end of the day, you should get to the same answer. It should always be the same answer. Inverses are unique. So, proof's not so bad. Since B is the inverse of A, we have, for example, if I say B times A, I would get the identity. We can multiply both sides on the right. Remember, it's matrix multiplication, so you always have to say if I'm on the left or the right, because it's not commutative in general. By C. This gives us B times A times C is equal to the identity times C. Associativity tells us I can multiply any two matrices in the product I prefer by moving the brackets. But A times C is the identity. Since C is also an inverse of A. And so what we have, B times the identity is just B, and so I get that B must be C. Right, so I have two separate matrices and they're both inverse of a matrix A. They're actually the same. There's only one. Inverses are unique. Let's talk about the second way to find inverses. Well, not the second way, a second way. We're only going to be doing two, and in general, it's up to you. I don't particularly care which method you choose. Do the method you like the most. Personally, I like row reduction better, but it's completely a personal preference. I'm not going to force you to do something one way or the other. First, we're going to need some definitions. There's something called the adjoint of A. Denoted with ADJA is defined as the transpose of the matrix cofactors of A. about the matrix of cofactors is this is the matrix obtained when each element is replaced with its corresponding cofactor. And we define cofactors. It's just the minors that you block out that row and that column, and then it takes the checkerboard of signs. So if A is something like A11, A12, A21, A22, A2n, all the way down to AN1, AN2, ANN, then its matrix of cofactors is C11, C12, C1n. CNN. So basically now what this amounts to doing is you're going to be finding a bunch of determinants to actually figure out an inverse. So let me tell you about anything else. No, I think that's it. So now, note. Direct computation will show you that the following is true. If I take A times the adjoint, I would have the determinant I mean, you can write out the computations for this, it'll be clear. If you use the row reduction definition I gave you for determinants, well, it's a matrix equation, so you can put the identity here to make it a matrix equation. Okay. So this means, assuming A inverse exists, I can multiply both sides by A inverse. Here. And we end up with this formula. Let's actually use it so you can see what it's talking about. In fact, let me derive something in general for you. It's a formula that they put in the book, but they never really told you where they got it from. This is actually, you could get it from row reduction as well, but this is actually probably one of the easier ways to get it. So your book tells you what the determinant of this guy is. One way to derive it, besides row reduction, which we could have just done row reduction as we sort of shown before, but we could actually compute this guy here. adjoint of A is equal to what? It's the transpose of the matrix of cofactors. So remember there's that plus, minus, plus, minus, plus, that checkerboard of signs. So in each case, you're going to have that plus for this guy, and you're going to replace A with its cofactor. So you block out everyone in his row or his column, and it replaces with the determinant of that guy, which is going to be a D. Do the same for B. It's going to be minus, block out everyone in his row and his column, get a C. Do the same for C. That's a minus, block out everyone in his row and his column, that's a B. Do the same for D. He's a plus, block out everyone in his row and his column, you get an A. Take the transpose of that, you get D minus C minus BA. And we know that the determinant of A in this case is just AD minus BC, which means A inverse by this formula is just 1 over the determinant, AD minus BC, times that matrix, D minus B minus CA. Let's our matrix A was 1, 2, 3, 4. So this means the inverse is 1 over 1 times 4 minus 3, 6. What I'm going to do is I'm just going to switch these two and change the signs of those two. So that's minus a half. So this gives us minus 2 plus 1. And that's 3 over 2 minus a half. You realize that's what we got last time. Okay, so that works. Let's do the other one. So we can see that we get the same answer. The other matrix was what? 1, 2, 3, 2 minus 1 minus 1, minus 3, 1, 4. Did we ever find the determinant of this guy?
No.
Let's find the determinant. Determinant of A is what?
1 times -4 plus 1.
Let's do some type 3 operations to make this easier. So I'm going to replace 2 by itself plus a multiple of another row, so let's multiply that by minus 2. So it's minus 2 row 1 plus row 2. So 2 minus 2, 0, minus 1, come again? Minus 1 plus that is a 3, minus 1, minus 6, right? Minus 7. If I take, now I'm going to leave this alone. So I want to leave row 3 alone, and then I'm going to add 3 row 1. So 3 times this is 3 plus that, 0. 3 times this is minus 6 plus that, minus 5. 3 times this is 9 plus that, 13. And so the determinant of that is just going to be plus 1 times the determinant of everything you get when you block out his row and his column. That's 3 minus 7 minus 5, 13, which is 39 minus 35, which is a 4. And the adjoint of A, I'm going to replace each guy by the transpose of its matrix of cofactors. So there's going to be a plus sign here. Block out everyone in the first row in the first column. I would get minus 4 plus 1. 3. Let's go to this guy. So if I block out everything in the first or second column, what do I get? 8 minus 4. So it's 4, but he gets a minus sign. This guy gets a plus sign. Block out everyone in that row and that column. That's a 2 minus a 3. Huh?
That one is wrong. Second entry.
I'm looking for the guy here.
That one is wrong. The second one. The one.
Oh, here? What did we get here?
8 minus 3. 8 plus 3.
No, it's 8 minus 3.
That's 5, right?
So it's minus 5. And then in the last one we get 2. In the last one we get 2 minus 3, right, which is a minus 1. And you continue this way. So I'm going to find the guy here, which he's going to take a minus sign, plus sign, plus sign, minus sign, minus sign, plus sign. Okay, so now I'm going to replace the 2, block out everyone in that row and that column. What do I get? Minus 8, minus 3. So minus 11. Plus 11. Replacing this guy, or in his row and his column, I get 4 plus 9. It's 13. To replace this guy, his row and his column, I get 1 minus 6. So minus 5, which changes this to plus 5. Replace this guy, block out everyone in his row and his column, I get 2 plus 3. So that's a 5 plus 5. Go with the 1. Block out everyone in his row and his column, I get minus 1, minus 6. I get a minus 7, which with a minus makes this a plus 7. Then the last one, I run this row and this column, I get minus 1 plus 4. So I get 3. Turn the first row into the first column. Second row into the second column. Third row into the third column. And so this means that the inverse of A is actually 1 over the determinant, which was 4, times this matrix. Is that what we got last time?
Yeah.
Just another way to do it. So that's another way to find an inverse. I mentioned this to you before. If A is invertible, then AX equals B has a unique solution. In fact, one of the ways to figure out what X is to multiply both sides by the left by A inverse. So one use of an inverse is actually to help us solve equations when we know that the coefficient matrix is a square matrix with a non-zero determinant. We can actually find the solution. Notice that I figured that out by multiplying both sides. let's actually do some examples of solving some systems with this method. So x plus 2y equals 5, 3x plus 4y is 11. That's my first example. X minus 2y plus 3z equals 1. 2x minus y minus z equals 0. Minus 3x plus y plus 4z equals 0. How are we going to do this? Well, notice that this is actually 1, 2, 3, 4 times xy equals 5, 11. This guy, I can let it be my a, this is my x, this is my b. But a I actually know the inverse of. Xy must be equal to a inverse times 511. What do we say the inverse was here? Now if you do that, I would get, in the first case, minus 10 plus 11. In the second case, I would get 15 over 2 minus 11 over 2. So what would that be? 1. And here I would have 4 over 2, which is 2. Right? Now we can actually check this. If x is 1, and y is 2, I get 1 plus 4, which is 5. If x is 1 and y is 2, I would get 3 plus 8 equals 11. So that's actually the solution. So you can see this, and you get that. Finding a 2 by 2 inverse is not that hard. You can even use just a formula, and then just multiply that guy by this guy. Now, if it's in the case where you have something slightly bigger and you already had to find the inverse of this guy from a previous problem, which now and again it happens, you could actually use that to your advantage. So here I'd have 1, 2, 3, 2 minus 1 minus 1, minus 3, 1, 4, times x, y, z equals 1, 0. This means x, y, z equals a inverse times this guy. And my a inverse was what here? Let's start with the inverse. Minus 2. No, this is the guy we computed, the long one.
Minus 3 over 4.
Minus 3 over 4.
11 over 4.
11 over 4.
5 over 4.
5 over 4.
Minus 5 over 4.
Minus 5 over
13 over 4. 7 over 4. Minus 1 over 4. 5 over 4. 3 over 4.
So if I take the inverse and multiply this guy, I would just get minus 3 over 4, minus 5 over 4, and minus 1 over 4. So inverses help us to solve equations. It's not the only thing they're good for, but it's one of the things that in chapter 1 we care about a lot, being able to solve equations, and we will care about that in general. So yeah. one more way to solve equations. We've seen it before, but I just want to mention it, write it down, so that we all know. And this would actually wrap up 2.3. It was the last thing in 2.3 that we didn't talk about. This is using determinants. It's called Cramer's rule. We saw this in algebra class. I actually a couple times on quizzes before, but right now I just want to actually officially state it for the class. Suppose we have ax equals b. Define where, for notation's sake, x equals x1, x2, all the way down to xn, b equals b1, b2, all the way down to bn, and a equals a11, a12, all the way down to an. And now define these three. Set D to be the determinant of A, and dxi equal to the determinant of B, where B is obtained by replacing the ith column of A with B. Right, so dx1 is you replace the first column of A, instead of A1, A blah blah blah. All in this line you have B1, B2, B3, B4, all of them. You're just going to replace that whole column. Then, here's what we can say about the solution. If there are a couple of cases. If D is non-zero, then AX minus B, AX equals B has a unique solution. Given by each component, you take dxi and you divide that by B. Another case, if D equals 0 and all other dxi equals 0, I mean every single other one is also 0 at the same time when D is 0, then AX equals B has infinitely many solutions. Lastly, if D equals 0 and some dxi not equals 0, like if one or more, if any one of these guys ends up being non-zero, then AX equals B has no solution. It's inconsistent in that case. This is called Cramer's rule. Your book has a proof, I'm not going to do it. I guess you can do a small example. I mean, it should be taken derivatives, but let's just do this small example. X plus 2y equals 5. Let's redo this guy. 3x plus 4y equals 11. This was the 2 by 2 system we had. Here, d would be the determinant of 1, 2, 3, 4, which was minus 2. dx would be the determinant of the x column. I'm going to replace with the b column. 5 to 11, 2, 4. Find the determinant of that. This is 20 minus 22. That's also minus 2. Find dy. I mean, I'm going to replace the y column with the b column. So this was 1, 3. Replace this 2 and 4 with 5 and 11. Find the determinant of that. I get 11 minus 15. Get minus 4. Since our b is non-zero, we know that x would be the same as dx over d, which is going to be minus 2 over minus 2. So your x value should be 1. Your y value would be dy over d, which is minus 4 over minus 2, which is 2, which we had last time. Okay, so computation, I think that's all we needed to cover. So we pretty much finished chapters 1 and 2. There's some properties that I didn't write down, but those are just things, you know, I might write them down next time or give you a printout or something, because it's a lot to write down. But here's how we're going to do it. So homework for 1.2.3, 1.4, 1.5, due Wednesday, as in 2 days from now. And the homework for the remainder of the chapter 1, which is 1.6, 1.7, that's due the Monday next week, a week from now. And I don't know what the dates are. So this is 3/11. Today's the 7th. That was the 9th. Okay, that's 3/9. This would be 3. What? Sorry. So, yeah, Wednesday we start the fun stuff. The not so computation stuff. All right, thank you. Doing interesting things. So yeah, you can read ahead as well for Wednesday's class. That might help you guys. Because it might be unfamiliar to a lot of you. I think that's vector spaces we're starting next. 418S. I have your homework there.